So sitting there over a glass of wine in San Diego, we said, okay, these are the constraints, these are the things, this is what you need, this is what we want. And we came up with the inverter.
So, good morning, everybody, and welcome back to the next episode of the Dental Implant Podcast. And today I'm actually really excited because I think I'm going to learn a lot as well. So for all you titanium nerds out there, this is going to be superb, okay? So I pride myself that, I educate myself a lot and I know a reasonable amount regarding implants. I have with me, joining me today, Graham Blackbeard, who is the founder of Southern Implants. Now, if you think I knew a lot about implants, we're about to melt your mind. So Graham, thank you very much for joining me on a Sunday morning. It is quite early here, so if I'm rubbing my eyes, it's because I've taken Archie out for a walk already and it's early. Do excuse me, it's literally a Sunday morning. So Graham, thank you very much for joining me today. And just to start, could you give us a little bit of a background with regards to how Southern Implant started? Because I believe you're actually an engineer. So a lot of the things that we're going to talk today, the level of engineering that goes into this is absolutely incredible. So if you wouldn't mind giving us a little bit about your history, that would be very, very much appreciated.
Certainly, Pav. Thank you very much for having me on this, and certainly hope that I can remember the right things at the right time. That's always the thing. So my background is mechanical engineering. I also then did a master's in industrial engineering and then went off to the University of Utah, where I worked for Willem Kolff, who was a Dutch guy that the Americans had recruited after the Second World War. He'd invented dialysis during the Second World War, and he then developed the artificial heart and various other items. So he probably taught me more than anybody else. This wonderful gentleman, Willem Kolff from Groningen in Holland, basically, but it was all out at the University of Utah. So then I came back and started a company to make artificial hearts and heart valves. So the original name of the company, which is now Southern Implants, was actually Cardiac Devices. The interesting thing is that we were making the housing for the heart valves out of titanium. And two prosthodontists contacted me almost within 2 weeks of each other, asking, they'd heard that I was making heart valves with titanium, and could we please help them with certain problems that they had. So the one was Peter Kemp, who'd done his prosthodontic training at the Eastman in London, and the other was Hannes Slabbert from the University of the Witwatersrand. They'd both been on training with Professor Bronemark in 1985. So this was now 1987, and they asked me if I could please help them with abutments. So I put my mind to it, went and found the literature, etc., and we made some abutments that they needed to finish off some cases that they were doing. And of course, within weeks, they came back and they said, "Can you please make us implants?" And the main part of this was that there were sanctions against South Africa from the United Nations because of the apartheid policies. So we had two dental schools who had been trained up in Sweden on dental implant therapy, and they couldn't get the Noble Biocare products, or it was at that time Noble Pharma, from Sweden, because the Swedes are very ethical guys. They didn't want to break the sanctions. Now, interestingly enough, the French and the Germans generally don't worry too much about sanctions. So you could get the product, but it had to come via Germany with an extra link in it and extra cost being added, because somebody knew that if they were going to break sanctions, they were going to make some good profit out of this. So there was a cost aspect to it, and then, of course, that. So we went ahead and we made the very first implants, and interestingly enough, the very first patient just before we were about to do the operation, they discovered that he was diabetic, completely uncontrolled diabetic. So we delayed that. So our very first patient, it took 3 months before they stabilized him and they got his diabetes under control. And he happened to be an Austrian. And so he had these implants, and I was so worried that maybe we'd missed something when we made these very first implants back in they were made in the beginning of 1988, that I actually, we put in one of ours, one Nobel, one of ours, one Nobel. So we filled his mouth with implants almost, thinking that maybe we'd missed something in the recipe to do these. Of course, they're all integrated very well. And then he moved back to Austria. And interestingly enough, 2 years ago, he ended up going to a dentist who is a Southern Implants customer in Austria. So we got the 30-year follow-up, basically, of this, which is just fascinating. So that's really how it all started and how it got going. So we do still have a cardiac company that makes cardiac devices, and that goes under the name of Glycar. But the main focus of everything that I did from then onwards was with dental implants, because it was right at the start of the growth of a new market. And when something's at that place, it just gives so much opportunity. So it was much more exciting than making artificial hearts.
For disclosure to anybody watching or listening, I use Southern Implants, but I have no financial affiliation with them. This podcast isn't being sponsored or anything like that. The reason why I'm chatting to Graham is because he is a wealth of knowledge, and we're going to get onto some of that in just a moment. Graham, just so that you're aware, when I first started my implant journey, I studied quite hard, and when I was first speaking to Steve, particularly about external hex, it was just like, it's such an outdated, unstable connection, and I thought that I knew more about implants than what I did. And as I started to research the data more and more, what I originally thought, I thought my understanding was here, and like Southern Implants was like 20 years behind, but it was actually the other way around. Is the level of precision of engineering that goes into this, and the misnomer with regards to external hex is incredible. And as I said, when I started to speak to Steve and yourself and other colleagues as well, there's so much that started to come out of the woodwork, and there's a number of things that I'd like for you to touch on. Firstly, it's with relation to the titanium that you use and how it differs from what most other companies out there are using it. And obviously the level of precision of engineering that you guys go to as well, because it is completely on another level. One of the reasons why we use Southern is obviously, I'm based at Evo Dental, and I can't fathom doing a full arch without the coaxis. Combine on top of that the MSC, the machine neck surface, and you and I have had conversations with regards to removing hydrocarbons and the benefits that gives. I just think it's a fantastic all-rounded system, and you also have site-specific implants as well. So there's literally nothing that I can't do without Southern Implants. So again, if you could give us a little bit of the history behind how that's all evolved, the engineering behind it, the titanium that you use, that would be very much appreciated.
With pleasure. Let me start with the titanium. It's not too special, but with everything, you're always wanting to do the very best you can. And as an implant manufacturer, the one thing that you have to do is to do the least harm to patients that you could possibly do. So we are putting an artificial material into the patient, and it's going to be there for many, many years. So the idea really is that you've got to do something that is as inert as possible. so that we do not want things that are going to be corrosive, etc. So one of the fundamental things there is that we want the most inert material. So if we're going to use titanium, we must go with pure titanium. Alloys corrode at a much higher rate than do pure titanium in this environment. Now, certainly there are other environments where the alloys are fine, but in the oral environment, in contact with blood, the pure titanium corrodes at a lower rate than the alloy. So that was sort of one of the fundamental things. The reason to use alloy, and why quite a number of manufacturers do use alloy, is that A, it machines better, so you can make a more precise part sometimes with it, and B, it is stronger. But it is only stronger in tensile strength. So on a single blow, it is stronger. So that means that if you design in the implant for Muhammad Ali, a boxer, where it will be a single blow onto his implant, then the alloy is the better thing because it won't break as easily. But most people, you design in them for masticatory function. So in other words, cyclic loading. And in cyclic loading, the pure material doesn't grow cracks as well as, or as badly, should I say, as does the alloy. So that's compelling reason to use for corrosion and fatigue resistance. The pure titanium is the better thing. So now, how do we get a pure titanium that is really strong? And for that, we went to so as you know, a lot of the titanium comes from South Africa. We do part of the processing here, and we turn it into lumps of product that has already been through 3 processes before it is sent off to one of the titanium producers. And so we formed a relationship with one of them, the best ones, near Philadelphia sort of area of the USA. And there we discovered that, with metals, it's still a little bit of a black art. They get this raw stuff that's come out of the ground, and they now do it, and then they get a batch. And each batch has slightly different properties. So the minimum property is the ASTM standard. But many batches are way, way better than that minimum standard. So the next thing was, well, why don't they just let us know when they get a really good batch? And then we'll buy from that batch. And then we could put it on our drawing. So I think we're the only company where we put on the drawing minimum tensile strength 920 megapascals, whereas the standard is only 550. So it's a lot higher than the standard. And all our fatigue testing, etc., has been done now on this, and it's on the drawings, and that's exactly what we use. And that gives us wonderful properties of fatigue resistance, etc. So just interestingly, a week ago, Professor Carlo Ferretti said to me, he came across a zygomatic case, 14 years it's been in the mouth, and these implants have broken. And he worries now about putting zygomatics in. The first point is that 14 years ago, we didn't have this material. So the material was probably 25 or 30% less fatigue resistant to the material of today. So had you used today's zygomatics, it probably wouldn't have broken. Now, the other reason that it broke, I think, is that it was misfitting prosthetics. But you might have got away with it with the higher strength than you did 14 years ago with a 14-year-old. So I think material, one's got to use the absolute best, and that does require that. So now the difficulty is, what if you need material and they don't have one of these batches that meets the 920 megapascal? So what we do is we keep about 10 years supply of titanium. So I said, rather than give my money to to an investment house to go and I'll invest in titanium, and this very special titanium. So we keep a huge store of it so that we can do that.
So even with the huge amounts of titanium just sat there in storage, it's supposed to be incredible.
So this also came up in our discussion when because we make the zygomatic implant for Straumann, and the question was, should we use the alloy with the zirconia in it, with the zirconium, sorry, not zirconia. And the answer is no, because this pure titanium has pretty much the same tensile strength. It's actually better in fatigue, and yet it's pure. And when you're doing things like zygomatics, which are very big, a large amount of surface area, you want to go for the least corrosive product that you could possibly have. So I certainly don't think it would be a wise idea to put titanium alloy into zygomatic implants simply because of the volume of titanium that you have. So that goes to that. Then I think your next question following the titanium was the other aspects of it that we go to. So one of the other things that we found is that the cutting tools are very important because they end up actually giving you your surface. And when you've got the MSC surface, which is a machined surface, what are we trying to do with that? We're trying to get a surface that is resistant to biofilm, as resistant to biofilm as those original Bronnemark implants, because we know that really worked incredibly well. You could have bone loss, and we're always going to get some bone loss just due to remodeling that we know is going to happen over time. As patients get older and older, the bone volume is going to decrease, and implants aren't going to stop that. So if we're going to have the top end of an implant or the coronal end becoming exposed into the soft tissues, we want to use something as inert as possible and something that the biofilm doesn't attach to as well. With a lot of the modern machining tools, we end up with surfaces that are a lot smoother than what Bronnemark did with those implants many years ago. And that is a problem, and that's where 3i ran into a problem when they did the machine surface. They were using modern tooling that actually left that surface too smooth for the attachment of the osteoblasts, etc. So in order to get an MSC, that machine surface at the top, to actually integrate well, you need to have a certain amount of machining roughness on that surface. So we had to go and take old Bronnemark implants and put them on the SEM, and our old implants that we made in 1988, which also had very, very stable bone levels on them, and have a look at exactly how that surface looked. Now, the interesting thing is that the cutting tools that were used in those days had a particular grain structure of the titanium, of the tungsten carbide. And as things have gone on, they've been able to refine that, and they make cutting tools that are much better, more efficient. But it doesn't leave you with the same surface. So we have to go back to getting tungsten carbide with a particular grain size to give us back that particular surface, because we know that works so well. And of course, it would take another 30 years to find out if maybe something different is right. But let's rather work with what we know. So, yes, and as a result, we make our own cutting tools so that we can control the surface that much better. So that is a critical factor. And most people will just buy cutting tools, but we've actually now got a tool room that makes the cutting tools so that we can control these things to just another degree.
This is one thing I find really interesting. It's not just, it's a machined surface. It's you need a machined surface, but we know it's a certain topography that gives us that balance between lack of biofilm adhesion, but permitting the osteoblasts to actually integrate onto the surface. And the modern tools are almost too good. They give too smooth a surface. So you've actually gone back, you've done the SEM analysis on the original Brannemarks, and you're like, right, we're going to replicate that. This is what I was saying to those listening and watching. This is the level of precision of engineering which makes me happy that I'm using Southern. It's not just, I want a machine surface. It's that we know, and I did actually have some Brannemarks that I needed to remove for a patient because I was redoing her case, and prosthetically they weren't in the correct position. And they'd been in her mouth for about 35 years, and they were really difficult to remove, and they were machine surface. So it's going back to knowing what works and replicating that, and not just going, we're going to program in a machine surface. So the precision of engineering is just incredibly important as well. It's just fascinating to hear, Greg.
And certainly, you pick up, you meet wonderful people, and you pick up great sort of nuggets of information. And Neil Meredith was someone who really helped us quite a lot. And he put us onto a machine that was developed by Olympus for surface characterization. And a lot of this we would not be able to do had we not got this particular confocal microscope. So SEM can do certain things which are very good, but it certainly can't do surface topography properly. For that, you need a confocal microscope. And Neil Meredith put me onto that. And that just opened up a complete new world of being able to really control your surface that much better. In terms of the contaminants, the carbon contaminants, etc., it's certainly something which we've been working on a lot of the time. And here we've got to either go in one direction or another, because there are two things that are pulling it apart. So the one way that 90% of manufacturers remove the carbon contaminants on the surface is with acid. So with acid, you can always remove all the carbon. But the problem is it leaves your surface more corrosive. So in the short term, fantastically good, because you now have this surface that's free of carbon contaminants. But in the long term, you're going to have a more corrosive surface, which is going to play problems with peri-implantitis later on. So yes, I wouldn't say that we've managed to get rid of all the carbon. We can, but then we're going to have a worse surface in the long term. So you've got to get a balance in between this, and that's what is the difficulty there, because you've got two things pulling in different directions for that. So one of the things with the corrosion is that we found out that the National Physical Laboratory in London, the NPL, they'd done a lot of work for the orthopedic industry, and had almost changed the orthopedic industry from using the common alloy, grade 5 titanium, because of the results that they got on this. So we said, okay, they've developed all the test methods, so let's rather go to this laboratory because they can do it. So we gave them implants from various manufacturers, including our own and some experimental ones, and we asked them to characterize these. There are three different ways in which you can measure corrosion fairly well, and they do give different results. And obviously, if one was a little bit unethical, you would only present the one where your product does the best. But you've got to look at them all. In the one particular test, ours was second best. Straumann was best. Probably because they pack it in, the SL Active is packed in saline, which does have an advantage in this particular test, only in this one test. And that is also the very fascinating thing that I've discovered over the years, is that you can test things in a lot of different ways, and then you only publish the one that shows that your product is the better one. And we did this with the University of California in San Francisco on a spinal product that we were developing. And they tested over a whole lot of things, and it didn't show that our product was that great, except in the one test. And they said, okay, well, this is the one we'll publish because it obviously shows that your product is superior. And I said, this isn't really that great. And they said, well, this is how research works, you do a whole lot of things and you only show the results that really are favourable to you. And you bury the other ones. Nonetheless, I don't like... Yes, it happens a lot, yeah. Then coming to Coaxis, fortunately we've had some wonderful people that have come to us with ideas, and we have a lot of things that don't really go very far, but you've got to explore a number of items. So Coaxis was certainly one of them, and that was Professor Dale Howes, who's now at the Department of Prosthodontics in Sydney, in Australia. And Dale came to me and said, I need this for screw retained. And he'd done a because of course there wasn't CBCT back in the early 2000s. So he'd done a cephalometric study, and he'd showed that if only he could get about 8 degrees of angle correction, he would have been able to avoid how many cases of where they had to cement, where they could have done the screw retain. So that was the motivation for it. And then the question was, yes, we could do 8 degrees, but if we did a few more degrees, and that's where we came up with 12, it would actually go to 100% of the cases. So that's where the 12-degree Coaxis came about. So, yes, certainly not us as a company that had done that. It was a very good-thinking clinician who had come and said, this is what I need. And in a similar way, it was sitting at dinner in San Diego with Steve Chu that he came up and he said, we love your Max implants in the posterior because we can get stability in an extraction socket. And they're just fantastic for us. But we need the same thing in an anterior extraction socket. But these are the factors that are pulling us in different directions. We want it narrow so that we have more bone. And he told me about the work of spray and how, dimension is so important, etc. So sitting there over a glass of wine in San Diego, we said, okay, these are the constraints, these are the things, this is what you need, this is what we want. And we came up with the inverter. so that's where it happened. Yeah. So it's really just a case of listening and trying to see what is possible. And also there's a good deal of luck that goes with it. So the Coaxis, interestingly enough, the concept of that was originally thought of by 2 German professors, Schilly and Hartmann. And we only discovered this when we were trying to get a patent on the Coaxis. So we thought that Dale Howes was the inventor because he'd thought of it without knowing about Schilly and Hartmann. It was only when we went to get the patent that we discovered that it had already been patented. So we then bought the patent from Schilly and Hartmann. So what happens is that people have these problems and they think of ways of doing it. But you've also got to have the technology to do it. Now, when Schilly and Hartmann conceived the Coaxis, machining technology was that to cut an internal screw thread, you needed a tap. And there were things called tapmatics that we used in the machine shop to cut threads. And you always had to have a few millimeters below where the thread went for the nose of the tap to go. But right in 2001, where Dale Howes had approached me to do this, I'd come back from a machine show in Germany, and I'd seen a Swiss company showing how they made these little cutters that you could now machine a thread to the bottom of a blind hole. And so the company in Switzerland is Glur, and they developed this tiny little cutter that had to, but now you also needed a CNC machine that had 8,000 RPM minimum speed because it's such a tiny cutter. So there were ingredients that you needed. And when Dale Howes was talking to me about this, I thought, with this new technology, we can do this. But had he come 2 years earlier, I would have probably said to him, "Oh, Dale, we can't do this."
Yeah.
But it was just the timing was all right. And that enabled us to be able to make coaxial implants because you needed to be able to get a screw thread to the bottom of a blind hole. So there's also luck that comes about or different things together. But you've also got to have a very good grasp of technology and requirement.
So for those listening
to put it all together,
don't know what a coaxial is, it's an incredibly very, very clever design. So a problem that we often have as surgeons is if we want to put the implant in the perfect position for a screw retained restoration, quite often the apex of the implant's poking out buccally, and you have to look at grafting procedures. Alternatively, you can put the implant within the bony envelope, and then you've got to do an angle correction using an abutment, then do cement retained. So there are problems either way. So what coaxial is the implant has an internal angle correction within the actual head of the implant. What this means is you can put the implant within the bony envelope and still get a screw retained restoration. And it is a workhorse for us at Evo. And it means that, we can put implants into perfect positions and have everything screw retained and not have to worry about angled multi-units, which cause their own problems. So for anybody listening to who wasn't sure what we mean by the term coaxial, that's what it is. It's an implant with an internal angle correction within the head of the implant, and it is very, very clever stuff.
Yeah, so a lot of luck goes with these things, a lot of knowing what technologies are around, and a lot of making sure you have all the right relationships in order to do these things. And then, of course, as the evolution of this goes towards immediacy, some of these things become very much more important because to do immediate full arches without the correct angles, you can do it. Yes, of course you can. But it just makes it so much more difficult, more expensive, etc. So some of these things just come about and help just that little bit in order to make the procedures go that much better. Then...
That's what I was just thinking, because I got so engrossed in what you were saying, I've lost track a little bit. I think again you've obviously touched on the level of engineering that you go to. I understand that your quality control and making sure that the implants are exactly as they're expected to be, that's incredible as well. Because when I was at the Zaga course last year with Carlos Aparicio, Stuart there, and he was going through, these are the steps that we include, because it's not just that your engineering is to a high standard, but your quality control is just as high. Is that correct, Graham? Would you mind going over that a little bit?
Yeah, probably we do things a little bit differently, and we always aiming to try and see how can you make this even better. We want to work with top clinicians like yourself. And therefore, what is that little bit of extra that you can do? Similar to the Formula One, they've all got rules that they've got to work by, but somebody's got to just do something a little bit better to get that extra little bit of speed out of the car, etc. So it's always just, what can we do a little bit better? So one of the things that worried me quite a lot was people would say, this one fits really well, but this one doesn't. And you look at that and you sort of look at the way that things are made. So the traditional way is that you tolerance all your components. So in other words, you've got a minimum and a maximum. And when you set up your CNC machine, you set it at the minimum, knowing that the tool is going to wear, and that as the next one comes out, it's going to be a little bit bigger, and the next one a little bit bigger because the tool is wearing down as it does it. So manufacturers work between the minimum and maximum tolerances. And therefore you get this. And you put your tolerances quite close. They may be, 50 microns or so. And generally that's how it is done. And all the manufacturers that we know, and I go to them because they often offer to make things for us, etc. So you go and you look at their factories and you see how they do things. And there's a lot of contract manufacturing going on. People come and they say, oh, we make the Nobel screwdrivers for them, or, can we make yours for you, etc., etc. So you go and you have a look at that. But what I've discovered is that the better thing to do is to set your machine up in the absolute middle of the tolerance band, and then to measure every part as it comes off the machine immediately. And then you make the adjustments and you try and keep it right in the middle the whole time. And then what you'll find is that, everything should feel the same because they all just around about the middle. But that does require that you have a operator who's actually an inspector at every machine, and he measures every part as it comes off the machine. So yes, a little bit of so we don't run machines through the night with nobody there, because there you have to set up at minimum and accept that it's going to go towards that. And in the morning you measure, and then you throw away the ones that don't quite make it. So we'd rather do it the other way around. We also then don't waste titanium because it's only when we set up a machine that we might get a few scrap parts. But once it's going, we measure in all the key components, so there is very little wastage. And that is also a
Instead of having a tolerance where you're like, we'll accept everything between here and here, you're actually tightrope walking, and you're keeping on that very thin tightrope, which is hard. So,
that's a fantastic analogy, Pav. Well done. That's exactly what we try. That's what we try to do. And I think it, from a long-term clinical outcome, will it make a difference? Probably not. But it's just, it's just striving to do something a little bit better.
It reflects back to, as a clinician, knowing that, well, actually, you know what, my implants are probably all just about the same, but they're going to be somewhere between here and here, versus actually, you know what, they're all along this line, so that tolerance is much closer together. That's just reassuring to know as a clinician. And again, this is one of the reasons why I use Southern. In fact, one of the reasons why I switched to Southern in the first place is because I wanted something with a machined neck based upon my dissertation for my master's, which is based upon hydrocarbon removal. And because I'm of the opinion we do not need treated surfaces at all. They are completely redundant. If you get rid of the hydrocarbons, you can get predictable integration. I think this is something that you and I have spoken briefly about as well. So that's actually one of the reasons why I switched to Southern. One of the reasons why I used external hex as well is because I wanted a wide range of coaxis available to me. And when I first started it, I was like, oh, okay, external hex. But again, the more I've educated myself, the more I actually understand, well, actually, external hex is a good connection if you know how to use it correctly. There's a lot of people not using it correctly, and then they blame the connection. But there are other connections that Southern have DC connection and different ones as well. And I've just the reason why my journey first started with Southern is purely because I wanted that machined neck, and then I've just gotten happier and happier as I'm going along, thinking to myself, they understand corrosion, they're using the right materials, the level of engineering is very high, and then then it's like, oh well, now I've started using Max, and I've got inverter available to me. It's just absolutely incredible to have a system which can do just about anything with that level of engineering. So it's been a fantastic journey for me as well. I've really enjoyed it, and I'm still learning. We've got Greg Boisvali joining our team in the next month or so, and I'm going to soak on his brain and get as much information from him as I can as well. He's a lovely guy. I've been chatting to him. He's a really nice guy, and I can't wait to learn from him.
Yeah. I think just in terms of that, I fully agree that, connections are totally overplayed in terms of their criticality to things. But external hex is more difficult to work with. It's the tactile feel of items is not that great. And you can't really make it taller because then you end up with other problems, etc. So I understand fully that it's not going to be the connection of choice for the majority of people placing implants. It's too difficult to work with. But for those who are prepared to and get the tactile feel of an external hex, then it's a good system. And yes, it gives you some other versatility with greater angles of coaxis, etc. A fascinating discussion that I had with Katja Nelson from Freiburg University a few years ago. Freiburg University had traditionally used external hex Brånemark implants for years and years. And then the wave of conical connections came across Germany, and they felt that they were completely antiquated and they were doing the wrong thing. So they then changed to conical connections. And things went fairly well in the beginning until they started looking back at cases now with conicals that had gone 10 years, etc. And they started seeing that their external hex results, longer term, were actually better. And they started questioning, why is this? And there have been a number of publications out of this group from Freiburg. And I think probably Blum, his publication with Katja Nelson in the authorship as well, is probably one of the most significant there. And that is that the conical connections do fantastically well in light loading situations. So in other words, in the anterior aesthetics, if you're going to do an inverter in the anterior region, I've got no problem in saying conical connection. It gives you a better platform switch, which gives you better soft tissue stability. The advantages to that conical connection in the anterior region. But when you start going to posterior with conical connections and you look at them over time, what happens is that they tend to open up slightly, which gives you a microgap. And they did testing, and the Blum paper is all about this. And they did testing on Ankylos, Astra, Nobel. There were four companies with the common conical connections. And they actually didn't use such high loads, but they put them on repeatedly, etc. And they found that these conical connections actually open up with time. And therefore, posteriorly, a butt joint is definitely the better thing to use if you want long-term stability of that connection, because a butt joint doesn't go anywhere. It just stays there. So butt joints at the back, and Straumann have got onto this with their BLX system, that the prosthetics that they sell you at the back don't use the conical connection. They sit on top of the implant to give you a butt joint. So they call it a conical connection, but actually they're using it as a butt joint in the back of the mouth, where your loads are highest. And we did the same before them. We did the same with our internal hex. We have what we call the platform matched range, which sits on the top of the implant, so that in the back of the mouth you use butt joints to give long-term stability, and in the front you can use external hex or internal connections, etc. But the conicals have the advantage of the bigger platform shift, which probably in the aesthetic zone might have just that tiny little bit of advantage. So that's where it is. So yes, you've got to know the differences and where they're good and why they're good. And thereafter, a big factor is what works well in your hands, what the
Yeah,
tactile feel
I think
of
this is something that Bill Schaefer and I
that's
discussed as
important.
well. Is
But there's nothing wrong with external
is,
use.
it's not the implant that works. The implant is just a tool. If you don't understand how to use that tool, or you don't develop your skills and have the mentoring to be able to use those tools, you can use any tool. You're not going to get the same results. So it's so training is important. Continued education is important. I pride myself on training and education. I'm still not done. I'm going to be mentored on zygomatics by Greg, and I study hard on it. My learning will never stop. And I know, Graham, you've got the same attitude as well. And when I speak to Greg and other colleagues of that caliber, they are always open to learning as well. So anybody listening, remember, I've always said that implants is a journey. It's not a learn, you do it, and and you're going to reach a peak. There's always something new to learn. So do remember that. It's as well as understanding the tools, you need to develop the muscle memory and have mentoring and the appropriate training to use these tools properly.
Definitely,
Yes.
and I absolutely, you are allowed to change your mind on issues, because as more scientific data
Yes.
becomes available, you all of a sudden realize that, I thought the following, but now that I've seen this new data, I've got to change my mind on this, and I've got to go and think in a different direction. And I think some people dig themselves into such a deep hole by saying, this is how it is, and they don't leave that opportunity to be able to change your mind
I
when
think part of
new
that's human
evidence
nature,
becomes
Graham,
available.
where particularly
and
if
that's what one's also
if you've
always got
believed
to be
for
able
something
to do.
for so long, and this data comes out that it says, well, actually, this is true. It is letting go of your ego almost to turn around and say, well, actually, what I've been saying for the past 10, 15, 20, however many years, I was wrong. This is what the data is suggesting now. But that's the nature of scientific development. For a long time, the Earth was flat. For a long time, the Earth was at the center of the universe. And as the data comes, we have to be open to it and interpret it and then move accordingly. Otherwise, we are doing ourselves a disservice, and we're doing our patients a disservice. So always read something with an open mind, critically appraise the data, and be open to changing your mind about things. What I believe to be true may not necessarily be what others believe to be true. I know plenty of people who are like, Pav, what are you doing with external hex? And they're getting incredible results with Morse tapers. But ultimately, if it works for the patient at the end of the day, I'm happy and confident with what I'm doing because it's my interpretation of the data. That's all that it comes down to.
Absolutely. And, I think the other thing is that one's got to look for fundamental data. And where I do that a lot is in the poster sessions of the conferences, of the major conferences. Now, of course, you can go online and you can read all this through there, and you can sift the data, because often that is the posters are often 3 years ahead of when the things are going to be published, and then a lot doesn't get published because it doesn't sort of fit with people's thinking or whatever, but often there's some very fundamental data there, and that's where I met Dennis Tarnow and Anne Wennerberg. Was walking around the posters, reading every single one at places like the AO and the EAO, etc. And we kept bumping into each other there because they also go and look at all this, what is really going on here. Just be a little bit ahead of the game, you need to do that. It's a lot of work and effort, but I find those just fascinating, and to find that and then find the person who did the research.
It's often the weird and wonderful that give you quantum leaps in what we're doing. Like the data that I was looking at with regards to conditioning of implants, I know that for machine surfaces, once I've conditioned the implants when they go in, that on a machine surface, I'm going to get 80% bone to implant contact ratio. This is why I am so confident that actually, we don't need treated surfaces. because the getting 80% on a machine surface is huge, and it's more than what we need for clinical success. And the data's been out there for a while. I just read it. That's all that it is. But there are some people who are starting to become interested in this. And from my perspective, clinically, has it played a positive role? Yes, absolutely. In my work, it has. I'm getting very stable bone around machine surfaces, and I'm very happy with that. So yeah, it's interesting stuff for sure.
And along that line, we've done a number of clinical trials and a lot of animal work. So we've worked with Rio Jimbo and Anne Wennerberg's group. We've placed implants into rabbits. We've done them into sheep, etc. All trying to find a good way to preserve that energy on the surface. So that you don't have to take your implant and then do a separate operation like you're doing to activate the surface or to remove the hydrocarbons. And
yes,
I must say that the results, these are expensive tests to do. And you go through all of this and you think, okay, we've cracked it. We've now going to have this 80% BIC on this, and then you find that no, it hasn't really. It's not statistically significantly better than what we've got, and that's the difficulty, is to maintain it in that state of hydrophilicity or surface activation in the packaging. So we've.
Again, speaking with regards to that as well, is I still get failures. I genuinely believe that any implant surgeon out there who says that they don't get failures, they're either lying or they're doing 2 implants a year. It's easy to have a 100% success rate when you're only placing 2 implants a year. Because even with all this, you get patients who come in and either they smoke, they haven't told you about it, they might be sick, there might be something else going on. So all that, whilst it's an unreasonable goal, my aim for my patients is to have 100% predictable integration and never have implants problems with the implants in the long term. Is it achievable? I don't know, probably not in my lifetime, but there's no reason why I shouldn't be striving for that. So that's the commitment that I make to patients. And you can go to all of these lengths and you still get certain patients where it's nice and easy and it's straightforward. You think it's going to be slam dunk case and the implant doesn't take. And then you get other patients where you're just like, oh God, the patient's going to sneeze and the implant's going to come flying out of their mouth. They're going to be back next week and the implants integrate. Dealing with the biological entity is a little bit more complicated than just the data. So everybody listening, please remember that.
Absolutely. And, the roughened surfaces are more forgiving. And I think that is, the other factor that with a very meticulous surgeon, yes, you could go back to machine surfaces quite happily. But for the lower common denominator or the average common denominator, probably you need the rough surface, and that's where the MSC is a good compromise, in that you've got the rough down there to keep the implant.
Graham, I really appreciate your time. I'll let you get on with the rest of your Sunday because I'm about to head off to the gym myself now. For those listening, it's if you want to know more, Southern have actually got a number of fantastic webinars on there, which are free to access on their website, going into all sorts of different things. So is check out the webinars. You'll learn a lot from them. Feel free to reach out to me as well. Always happy to discuss things. And you know what, Graham, I knew I was going to learn a lot from you today, and I have. Thank you so much for your time. Thank you so much. So if there's anything else that you'd like to, so if there's anything else that you'd like to say before we wrap up, please do let us know.
Thanks. It's been lovely chatting. No, well, I think as always, we just interpret what we see as the need from the clinicians. So keep talking to us. Tell us what you need, and let's see what we can do. And hopefully there's always some new technology out there to be able to do something better. We've never got to the end of the race.
Thank you, Graham.
It's always trying to do
the rest of your
better,
Sunday.
and that's what it's all about. So thanks so much for the opportunity.
Take care. Bye-bye.